This lecture is about one of the core concepts in mathematics, namely numbers, in fact whole numbers or integers, such as 1, 2, 3, 4, and so on. Now, the study of the properties of numbers is usually called number theory, and it's a vast and fascinating field of mathematics. It's also sometimes called higher arithmetic. And among the whole numbers or integers, the primes are particularly important, and I'm going to soon define and introduce them. It turns out that there's great difficulty in proving even relatively simple results in number theory. And this caused the great German mathematician Carl Friedrich Gauss to remark that it is just this which gives the higher arithmetic that magical charm which has made it the favourite science of the greatest mathematicians, not to mention its inexhaustible wealth, wherein it so greatly surpasses other parts of mathematics. Gauss is often known as the prince of mathematics, and he called mathematics the queen of the sciences, and considered number theory the queen of mathematics. And it's from Gauss that I took the title of the lecture. I will start by introducing and defining the prime numbers and giving some examples. Then we will quickly see their importance, as they are the building blocks from which all the other whole numbers are constructed. This result is called the fundamental theorem of arithmetic. One of the most crucial questions about primes is how many are there? And the answer to this question is given by one of the most beautiful proofs in all of mathematics. The proof was given in Euclid's Elements, which featured so prominently in my last talk on geometry. The rest of the lecture is in three parts. First, we will look at some approaches to finding or generating prime numbers. Then we look at some properties of the primes that show how random and unpredictable they are, or seem to be. Finally, we look at the primes in a different way and show how predictable they are, and introduce what is called the prime number theorem. And in discussing the prime number theorem, I will introduce one of the most intriguing and important functions in all of mathematics, the Riemann zeta function. This function lies at the heart of one of the most intriguing and difficult questions in mathematics, the Riemann hypothesis. The question is, do all the solutions of a certain equation have a particular form? And the full statement that I'll come to at the end of the lecture and say more about is, do all the non-trivial zeros of the Riemann zeta function have real part a half? Now, answering this question could win you $1 million. It was worth coming. The $1 million prize is offered by the Clay Mathematics Institute, now based in Oxford. And the solution to the Riemann hypothesis is one of the 7 problems that were originally posed. One of these 7 problems, the Poincare conjecture, has now been solved. The Clay Mathematics Institute proposed the prizes because, as they say on their website, the prizes were conceived to record some of the most difficult problems with which mathematicians were grappling at the turn of the second millennium. To elevate in the consciousness of the general public the fact that in mathematics the frontier is still open and abounds in important unsolved problems. To emphasize the importance of working towards the solution of the deepest, most difficult problems, and to recognize achievement in mathematics of historical magnitude. If you want to find out more, the web address is on the handout available at the end of the lecture. And in the lecture, I will end by showing you how the Riemann hypothesis is related to prime numbers. Now, to start at the beginning with what is a prime number. So a prime number is a whole number greater than 1 whose only factors are itself and 1. So examples, to let you absorb the definition: 2, 3, 5, 7, 11, 13, 17, 19 are prime, but not 9 equals 3 times 3 because it has factor of 3 divides into it, or 15 equals 3 times 5 because it has factors as well. Or I would know you would want to know 2013, this year's date, is not prime. 3 times 11 times 61. Also, next year's date is not prime because 2 is the only even prime, and 2014 is divisible by 2. And 2015, the year after, is divisible by 5. 2016 again is not prime, but 2017 is going to be a prime year. Now, the primes are the building blocks from which all other whole numbers are constructed. This result is so important that it's called the fundamental theorem of arithmetic. Every whole number can be written as a product of prime numbers in only one way, apart from the order in which they are written. So 30 is 2 times 3 times 5. It's the product of 3 prime numbers, 2, 3, and 5. And no other collection of primes can be multiplied together to give 30. 48 is 2 times 2 times 2 times 2 times 3. And just to show you, 22,012,013 is 19 times 53 times 21,859. Not to show it doesn't cheat when you get larger numbers. And this also gives you one of the reasons why we don't count 1 as a prime, because if we took 1 as a prime, then this fundamental theorem of arithmetic would not hold, because, for example, you could write 15 as 3 times 5, or 3 times 5 times 1, or 3 times 5 times 1 times 1, etc. So it's tidier to exclude 1 from being a prime. Right. So, how many prime numbers are there? Here I've listed the prime numbers up to 100. 4 up to 10, then another 4 up to 20, 2 more in the 20s, 2 in the 30s, 3 in the 40s, 2 in the 50s, and then up to having only 1 in the 90s. So writing it out like that, in case you might think they're going to end and there'll be a dearth of primes. But it turns out that there are an infinite number of primes. And the proof of this result, I think, is one of the most celebrated and famous in all of mathematics. It's also one of the most beautiful. Now, how could you go about proving it? By it, I mean that there are an infinite number of primes. Well, the most obvious way, I suppose, would be a constructive kind of way to find some sort of formula that would generate the primes, and if not all of them, at least enough of them to show that there were an infinite number. But it turns out that that's incredibly difficult to do. And we'll be looking in a few minutes at some of the approaches that we're taking as to how to go about generating prime numbers. The way of approaching it is due to Euclid, and it is based upon proof by contradiction. And Euclid first did it in the Elements in Book 9, Proposition 20. And there he proves there are an infinite number of prime numbers. And he does it by contradiction. He assumes that there are only a finite number of primes. And, well, Euclid assumed there were only 3. I'm going to stretch you a little bit further than that. I'm going to assume that there are n primes. P1, P2, P3, P4, P5, P6, up to Pn. But whatever it is, there are a finite number of them. We can write them down because there's a finite number. And then we construct this very clever number, n, which is the product of all the primes now. Remember, there's only finite number of prime number plus 1. The product of all the primes plus 1. This number is not divisible by any prime because P1 can't go into it because of the clever bit of adding the 1 onto it. P2 does not divide into it. P3 does not divide into it. P4 does not divide into it. So none of the primes P1, P2, P3 up to Pn divide into it. But remember the fundamental theorem of arithmetic. That told me, and you all nodded, I saw it, even though it's the lights in my eyes up here. You all believe that every number is a prime or made up of primes. That's what the fundamental theorem of arithmetic says. So n is a prime, either is a prime not in the list, or is made up of primes not in the list. In either case, we've got a contradiction, and our original assumption must be false. There cannot be just a finite number of primes. There must be an infinite number of primes. And let me, because of the algebra within this, or the way it's represented, look at a couple of concrete instances to show you that both of these cases can apply. Assume that the only primes are 2, 3, and 5. And construct the clever number 2 times 3 times 5 plus 1. But we can evaluate it, and it gives you 31. And what is 31? It's a prime not in the list. Assume the only primes are 2, 3, 5, 7, 11, and 13. And let n again be their product. 2 times 3 times 5 times 7 times 11 times 13. Add on 1, and you get 30,031. You break that up into its factors, and you get 59 times 509. 2 primes which are not in the original list. So if you assume that there's a finite number of primes, you can show a contradiction. So we've got an infinite number of primes, so we've got no worry that they're going to run out. And I'll just show you the Euclid proposition 20 in book 9, where Euclid does it for 3, but he does it for lengths, and his numbers are represented by lengths, and his numbers are measured by primes rather than divided by primes, but it's essentially the same argument over 2,000 years ago. So anyway, now that we know that the primes go on forever, let us look at attempts to find or generate some of them. And possibly the oldest attempt dates from around the 3rd century BC. It's named after the Greek Eratosthenes, who also, by the way, estimated the circumference of the Earth, and it's called the sieve of Eratosthenes. So illustrated by finding all the prime numbers up to 100. What we do is we write down all of the numbers up to 100 and delete the number 1. Then we put a circle around 2 and leave it, but delete all the multiples of 2. There's the circle around 2, and then all the multiples of 2 are deleted, the 4, the 6, the 8, the 10, the 12, all the even numbers beyond that. Then you look at the smallest number that's left. That's 3. That also is prime. You put a circle around 3 and delete all the multiples of 3. 6 had gone, but 9 now goes. All right, 21 now goes. You continue. It's so restful. It's very relaxing. The lowest number, 5, put a circle around it, eliminate all the multiples of 5 in the table. And then, finally, you put a circle around 7 and delete all the multiples of 7 in the table. And we don't have to go any further. What we're left with now are all the primes up to 100. And the reason we don't have to go any further is very nice. Because if you take, for example, 91. 91 is 7 times 13. So it's a multiple of 7. So it's already been deleted. And in fact, if you take any number smaller than 100, which breaks up into prime factors, one of those prime factors has to be less than 10. They can't both be bigger than 10, or their product would be bigger than 100. So if you've got a number that's less than 100, one of its prime factors has to be less than 10. So it's already been scored out, because we were scoring out the multiples of all the numbers less than 10. And in general, we only have to score out the multiples of primes up to the square root of the number that we're looking at. So 100, the square root of 100 is 10. If we wanted to find all the prime numbers up to 10,000, then we would only have to score out the multiples of the prime up to the square root of 10,000, which is 100. So it's a relatively effective way of finding the primes. It doesn't exhibit them explicitly, it gives you a way of being able to find them. But is there a more direct way of generating primes? This is an approach taken by the great Leonhard Euler. He was one of the most prolific mathematicians of all times. He produced over 800 books and papers in a wide range of areas, from such pure topics as number theory and the geometry of a circle, via mechanics, logarithms, infinite series, and calculus, to such practical concerns as optics, astronomy, and the stability of ships. He also introduced the symbol E for the exponential number, f for a function, and I for the square root of -1. In the words of the French mathematician Laplace, read Euler, he is the master of us all. And he came up with this quadratic, a very simple expression, n squared plus n plus 41, which has the following amazing property. That if you evaluate it, work out what it is at the number when n is equal to 0, so that's 0 squared plus 0 plus 41, giving you 41, you get a prime number. When you work out what it is when n is equal to 1, 1 squared plus 1 plus 41 gives you 43, another prime. When n is equal to 2, 2 squared plus 2 plus 41, that's 6 plus 41 is 47. It's harder to do the adding up when you're standing up here than if you're sitting down there. When it's 3, 9 squared plus 9 plus 41, giving you 53. Up to n equals 39. It generates prime numbers. They're not the ordering of the prime numbers, but it gives prime numbers. Well, it doesn't go on forever. When n equals 40, it gives you 1681 when you evaluate it, and that's not a prime, it's 41 squared. And you can see why this approach is not going to work for everything from the next one when n is equal to 41, because then you've got 41 squared plus 41 plus 41. Every factor is divisible by 41, so the whole thing is. Another attempt at generating primes was suggested by Fermat, Pierre de Fermat. He spent most of his life in Toulouse as a lawyer. He considered mathematics as a hobby. He published little and communicated with other scientists by letter. Fermat was the first important European number theorist since Greek times, and he resurrected the subject with stunning results. His other main area of interest was analytical geometry, which he helped to found. And Fermat conjectured that if n is an integer, then this more complicated expression, 2 to the 2 to the n plus 1, is prime. Now, to work this out, one starts with the 2 to the n and evaluates that, and then works out 2 to that power. So, for example, when n is equal to 1, we work out what 2 to the power of 1 is, that's 2. So then we work out 2 to the 2, which is 4, plus 1 giving you 5. When n is equal to 2, you work out the 2 squared, giving you 4, 2 to the 4 is 16, and 1 is 17. And this is one where you can tell the difference, 2 to the 3. We work out 2 to the 3 first of all, which is 8. 2 to the power of 8 is 256, and adding on 1 gives you 257. And each of those 3 is prime, as is the fourth one, which is 65,537. But Fermat was mistaken in assuming that his formula worked for subsequent values of n. These numbers get very big very quickly, because when you put n equal to 5, the number you get is 2 to the power of 32 plus 1. 2 to the power of 5 is 32, 2 to the power of 32, and that is that number, which is 4,274 million. I think it may be over 4 billion if we're taking a billion as 1,000 million. And that's divisible by 641. Remember, in Fermat's days, there were no computers around, but this was shown by Euler again over a century later. And no other Fermat number has been shown to be prime. So it worked for the first 4, but then not very successful after that. Right. My third example, of generating primes is due to the Baron Mersenne, a Mennonite friar who lived near Paris in the early 17th century. He believed the scientific discoveries should be made available to all. With this aim, he carried out an extensive correspondence with most of the leading European scientists of his day, acting as a clearinghouse for new scientific results. He also initiated regular meetings in Paris at which mathematicians could meet to discuss their latest findings. And these meetings led in 1666 to the founding of the French Academy of Sciences by Louis XIV. Now, a Mersenne prime is a prime of the form a power of 2 minus 1. So we're looking for primes whose form is a power of 2 minus 1. So let's run through some of them. If we let n equal to 2, we get 2 minus 1, 2 to the power of 2 minus 1, which is 3. Then n equal to 3, 2 to the 3 minus 1 is equal to 7. You will notice that 5 has not been obtained. 2 to the 5 minus 1, it's 32. Take away 1 is 31. 2 to the 7 minus 1 is again prime, 127. But if we raise 2 to the 4, 2 to the 4 minus 1 is 15, which is not prime. 2 to the 6 minus 1 is 63, again, which is not prime. So it turns out that the exponent n must be a prime for 2 to that power minus 1 to be prime. So that is a necessary condition. The power or the exponent has to be prime. But it turns out that it's not sufficient. So we have to have the exponent of the power being a prime, but it's not good enough to guarantee that 2 to that power minus 1 is prime. And an example of that is 2 to the 11. If you look at the middle of the slide, not all prime n make 2 to the n minus 1 prime. It has to be a prime number, but as I say, it doesn't guarantee that it gives you a prime, because 2 to the 11 minus 1 is 2047, which you've quickly factorized as 23 times 89. But they are useful because there's a very straightforward, computationally straightforward, still takes time, to check whether or not a number of this form is prime. So people who are hunting for the largest primes found so far have got that one. At least that's what it was when I looked up on the internet on Sunday. It's 2 to that power there. And that has got 13 million digits. Sorry, this is wrong. It doesn't have 13. It has 10,000 billion digits. 10,000 billion digits. And what I meant to write in that last line is that if you were to write it out on a strip of paper, okay, some of you may have smaller handwriting than me, or larger handwriting, or whatever, but it goes for about 1 million miles. A big number. It's not known whether or not there are an infinite number of Mersenne primes. There's an awful lot you can say in number theory that is not known. And they certainly don't give all the primes. You may have noticed the method did not give 5. Skipped over 5. But there is a most remarkable expression for generating primes. Not only generates primes, but it generates all of them. And that is this. And I always wanted to say this. Consider the following polynomial in 26 variables. A, B, C, D, up to Z. And that is it, taken from a work that the previous professor of geometry, Robin Wilson, delighted to see in the audience, and I worked on together. Not this result, sorry, a book in which this result appears. So K, WZ, you see WZ plus H plus J minus G all squared. And what you do is you let the variables A, B, C, D up to Z run through all the non-negative integers, give them all non-negative values, whatever one you happen to choose. And sometimes this expression will evaluate out to be a positive answer, and sometimes it will evaluate out to be a negative answer. The amazing thing is that whenever it's positive, it's prime. And even more amazing, every prime can be obtained in this way. Doesn't really help you very much. But it's one of those amazing things that can keep you awake. So the positive values, as it says there, are prime numbers, and every prime number can be obtained in this way. All right. Now, let's look at what happens when we start adding or subtracting primes. This gives us some of the most intriguing, difficult, but easily stated problems in mathematics. For example, if we add two prime numbers other than 2, we always obtain an even number. That's because every prime number apart from 2 is odd. And if you add two odd numbers together, you get an even number. But can we get all even numbers in this way? That's the Goldbach conjecture. Can every even number greater than 4 be written as the sum of two primes? And here I put down some examples. 8 is equal to 3 plus 5. 10 is 5 plus 5. It's also 7 plus 3. 20 is 7 plus 13. It's also 17 plus 3. 200 is 7 plus 193. 2040 is 119 plus 1021. This has been checked up to an amazing number, 4 by 10 to the 18. That's 4 followed by 18 zeros, and is found to be correct. But nobody has any idea as to whether it's true or not for every even number. That's what I meant by difficult, but yet easily stated. So Goldbach's conjecture is, can every even number greater than 4, greater than or equal to 4, be written as the sum of two primes? Now, quite remarkably, there is a result that's, I think, the best we have so far, due to Jingrun Chen, who proved in 1966 that all sufficiently large even numbers, that is, all even numbers big enough, are the sum of a prime and the product of at most two primes. So far enough out into the integers, there's a point beyond which we can prove that every even number can be written as a prime plus at most the product of two primes. Let me turn to another result. The Goldbach conjecture was concerned with adding primes together, and we obtain another tantalizing conjecture if we think about subtracting primes. Now, the only primes that are 1 apart are 2 and 3, because all the other primes are odd, so must be 2 or more apart. But how many primes are exactly 2 apart? And twin primes are a pair of primes which differ by 2. And if you list them out, 3, 5, the first prime pair, 5, 7, 11, 13, 17, 19, 29, 31, and going up like that, 107, 109, 2027, 2029, 1,037, 1,039. Are there infinitely many such pairs? After all, you saw almost a one-slide approach proof to show that there were infinitely many primes. But nobody knows whether or not there are infinitely many prime pairs. And up to 10 to the power of 16, there's that remarkable number of prime pairs. But the belief is that the primes, like London buses, can come in pairs. But they don't come in threes. Primes don't come in threes. And a prime triple, except for one exception, is a collection of 3 primes of the form n, n plus 2, and n plus 4. And the only prime triple is 3, 5, and 7. Right? And the proof is homework, which will not be marked. But I've given you a hint. Whenever n is not 3, then one of the numbers, n, or n plus 2, or n plus 4, can be divided by 3. And if one of them can be divided by 3, of course, it's not prime. And that's a question that used to be asked at interview. All right. we've seen that the primes occur forever. So as we walk through the integers, we're always guaranteed to have a prime ahead of us. We've also seen that it's difficult to say where that prime is going to be, but we know there's going to be one. And indeed, it seems likely that there's going to be a twin pair ahead. But it's not been proved that twin primes, twin pairs, occur forever. On the other hand, we can find a run as long as you like where on our walk where there are no primes. You have to go quite a distance before you find such a run, but you can find it. And that's a neat little argument that makes use of the factorial function. And here, the factorial function takes a whole number, and 2014 factorial is 2014 multiplied by all of the integers less than it. So, and let me do it for an easier one. Factorial 3 is 3 by 2 by 1. Factorial 4 is 4 by 3 by 2 by 1. Factorial 5 is 5 by 4 by 3 by 2 by 1. So the thing about this very large number, because it's all of these multiplied together, is that it can be divided by 2014. It can be divided by 2013. It can be divided by 2012, 2011, and you're getting the pattern. It can be divided by 4, by 3, by 2, and by 1. So now let me construct the following run of numbers. There's this big number, 2014 factorial, plus 2. That number plus 3. That number plus 4. That number plus 2014. If you look at the number, it can be divided by 2, because 2014 factorial can be divided by 2. It can also be divided, 2014 factorial plus 3 can be divided by 3, because 3 divides into 3, and 3 divides into 2014 factorial. The next one can be divided by 4, because 4 divides into each of the terms, the 4 and the 2014 factorial. Right the whole way down to the last one in the sequence. So there we've got a collection of numbers, a run of numbers. There are 2013 of these numbers. I chose that because it's this year's date. So 2000, and you thought might seem somewhat random, and none of these 2013 numbers is prime. So if you give yourself an integer, no matter how big, you can do this, take this approach, and you'll find a run of numbers of that length where there are no prime numbers. It will be way up the integers, but there's a run of that length with no primes. Okay. The number theorist, Don Zagier, at his inaugural lecture at Bonn University in May 1975, said, "There are 2 facts about the distribution of prime numbers of which I hope to convince you so overwhelmingly that they will be permanently engraved in your hearts. The first is that despite their simple definition and role as the building blocks of the natural numbers, the prime numbers belong to the most arbitrary and ornery objects studied by mathematicians. They grow like weeds among the natural numbers, seeming to obey no other law than that of chance, and nobody can predict where the next one will sprout." But then, he went on to say, the second fact is even more astonishing, for it states just the opposite, that the prime numbers exhibit stunning regularity, that there are laws governing their behavior, and that they obey these laws with almost military precision. But to talk about the second fact, we need to change our point of view, and we need to change the question that we're asking. Instead of looking at individual primes, or a formula for primes, we count how many primes there are up to each integer, and see if there's any pattern in the results. So I need to introduce the prime counting function, pi of x. Now the pi here is traditional, but it's got nothing to do with the number pi that arises as the ratio of the circumference of a circle to its diameter. I've done some calculations of the first few values. Pi of 10 is to count the number of primes that there are up to 10. And there are 4 of them, 2, 3, 5, and 7. Pi of 20 is equal to 8, as there are 8 primes up to 20. 2, 3, 5, 7, we have already, 11, 13, 17, and 19. And pi of 100 is 25, and this is from the sieve, which it took me a while to draw, so I wanted to use it again. And there are 25 primes up to 100. So what I want to look at now is to represent that graphically and to draw a graph of pi of x for values of x from 1 up to 100. And you get the staircase type of function. And as you go up this staircase or go along this staircase, you go up one every time you come to a prime. That's why it's got that jagged impression. That's why it's got the jagged feature. So it begins at 0, jumps by 1 at every prime number, so jumps by 1 at 2 and at 3 and at 5 and 7 and so on. So although there are oscillations, the function grows quite regularly. Now I want to show you the graph of that function, not between 0 and 100, but between 0 and 50,000. That is quite amazing. And Don Zagier says that the smoothness with which this curve climbs is one of the most astonishing facts in mathematics. In the next bit, I want us together, joint enterprise, to find a formula or postulate or conjecture a formula describing that curve. So let's go. Table might look a little daunting, but I'm going to take us through it in a gentle manner. Down the left-hand side, I have the values of x, and we're going to be counting the number of primes less than x. And what I've done, x starting at 10, then 100, and then 1,000, and then 10,000, 100,000, a million, 10 million, 100 million, a billion, and so on. So you can see what's happening there. We're looking at patterns. I'm increasing the value of x by 10 each time. Now the next column is the one where I did all the work. I have counted all the primes up to the value of x in the left-hand one. And it was easy to start off with 4, 25, 168, up to 10,000. There are 1,229, and then it got a little bit harder. 9,592, 78,498. So this is counting the number of primes, and up to the last one there, which is 10 billion, there are 455,052,512. Now that took the time to get that done. Can you imagine just how many hours, tedious hours, were put into doing that there? So this is like experimental mathematics that we're doing. Right? So if we started to say, we're looking for what happens for x as x gets bigger and bigger, I should tell you, rather than what happens down around the low levels. So that up to about 1,000, the third column is telling you what the proportion of primes are. So up to about 1,000, a sixth of the numbers are prime. That's what the 6 is in column 3. Up to 10,000, an eighth of the numbers are prime, about. Up to 100,000, 1/10 of the numbers are prime. Up to the next number, which is a million, a 12th, a 15th. Up to 10 billion, 1/22. Now what we see there is something very interesting in the third column. As x is getting larger, look at the numbers. And can you see any regularity in them? Not at the start, but once you go from about 10,000, you go from 8.1 to 10.4. Do your subtraction. You go from 10.4 to 12.7. Do the subtraction. Have you seen that answer before? From 12.7 to 15, subtract them. From 15 to 17.4, not quite the same. Each time, it's going up by 2.3. About 2.3. So when x increases by 10, the proportion of primes goes up by 2.3. Now that's something that you may be familiar with. That's exactly the property of logarithms. That if you increase something by a multiplicative factor, the logarithm increases by adding something on. And I've calculated in the fourth column what the logarithms of x are to the base 10, because they're very easy to do. Because to the base 10, what a logarithm is just what power of 10 is it? So the logarithm of 10 is just 1. It's just 1 power of 10. The logarithm of 100, which is 10 squared, is just 2. The logarithm of 10,000 is just 3, because it's 10 cubed, and so on. So that's all the fourth column is. But it turns out that the logarithm we have to take the base to is not 10, but it's this number e, the base of natural logarithms, just another number, it's just not 10. And then you see that if we take the logarithms to the base e, you get the fifth column, and the fifth column is just the fourth one multiplied by 2.3. So that's all that's happening as you go down this column here. It's just the column to the left multiplied by 2.3. 1 times 2.3, 2 times 2.3, right? All right, you've been very good, very patient. We have 2 columns. I want you to pick out the third and the fifth. The third is the proportion of the primes up to a certain number. The fifth is the logarithm of that number. And when you look at the 2 columns, would you say they're in pretty good agreement? Here we have 10.4, 11.5, 12.7, 13.8, 15, 16.1, 17.4, 18.4, 19.7, 20.7, 22, and 23. And in fact, the prime number theorem, this is experimental mathematics, the prime number theorem, I've just picked out those 2 columns, this is the third one, this is the fifth one, was conjectured by Gauss, and it says that the ratio of the 2 numbers, the number in the third column to the number in the fifth column, goes to 1 as x gets large. So the ratio of the logarithm to the proportion of primes goes to 1. And we can rearrange this to get, algebraically, if you multiply above and below by pi of x and divide above and below by log of x, it can be just re-expressed as pi of x over x log x, because it's the pi of x that we're concerned about, and you often see the prime number theorem written this way. Pi of x, and this symbol here, just means that the ratio of the 2 things goes to 1 as x gets larger and larger and larger. And Gauss conjectured this when he was 15. He studied tables of primes. And during his life, he once wrote how he would very often use an idle quarter of an hour to count through another chiliad, that is an interval of 1,000 numbers here and there, until finally he had listed all the prime numbers up to 3 million and compared their distribution with the formula that he had conjectured. Namely, that the ratio of the numbers of primes up to a value x divided by x over log x approached 1. The theorem, however, was not proved until 1896, when it was established independently by the French mathematician Hadamard and the Belgian mathematician de Vallée-Poussin. Right. Quite amazing to have conjectured that at the age of 15. But you see, it's an experimental result where he was looking at the ratio of the 2 things, and if you had the pattern, then you can see how to go on. Later on, he improved his conjecture somewhat. Oh no, sorry, I wanted to do what Legendre did first of all, because you were probably irritated the way I was when I first saw that, in that there's a sort of obvious way to make there be a better match. I said to you, look how close these 2 columns are, 15, 16.1, 17.4, 18.4, 19.7. And like me, you were probably dying just to take 1 off this here in order to get a better agreement. And that's what Legendre did. His, taking decimal points, the factor was 1.08366, which gives you a better agreement. But more importantly was a refinement of Gauss to it. Here's what he originally had. This is saying that the proportion of primes, pi of x divided by x, looks like 1 over log x. And he later had a better approximation here, which is what's called, for those of you who know the calculus, it's called the logarithmic integral. But an interpretation of this, which turns out to be quite important to conjecture estimates, is that this can be interpreted roughly as saying that the probability that a certain number is prime is 1 over the log of the number. Now, when I say roughly, that's because it doesn't really make any sense, because a number is or is not prime. But the way that this is coming out is that in the sort of interval concerning a number or surrounding a number, the probability that you'll find a prime over there is 1 over the log of the number. And that, as I say, that can be very useful in conjecturing estimates. Okay. So now we have the prime number theorem, and I want to finish with introducing the Riemann zeta function and its connection with prime numbers. Then you can start on your work to win $1 million. Well, first of all, I want to begin with a remarkable observation of Euler. But first of all, remember the fundamental theorem of arithmetic, that every whole number can be written as a product of primes in only one way, apart from the order in which they're written. So we've had that. And then I want to look at a particular series, the harmonic series, so called because of its relationship to music and overtones and harmonics. And Euler had this most marvelous observation, which you might think looks absolutely horrible when you first see it, and then you will think that it's so beautiful and pretty when I talk about it. It expresses this harmonic series as the product of some other series. The harmonic series as a product of other series. I know it looks terrible, doesn't it? But the time it took to put this onto PowerPoint is in itself a marvel. Now, remember your fundamental theorem. What we have got down here is a series which consists of the sum of the squares of the reciprocals of the prime 2. A half squared, half cubed, a half to the fourth. Here you've got exactly the same thing for the prime 3, the sum of the reciprocals of the different powers of 3. Here you've got exactly the same thing for the prime 5, for the prime 7, and for the prime 11. Right. Why are the two of them equal? Well, pick any number in the first series. At random, I have picked 1 over 42 because that's the one that happens to be in blue. And 42, what are the prime factors of 42? 2 times 3 times 7. So what we do is we take the first term in the first series, the second term in the first series, a half, the second term in the second series, a third. We take 1 from this next series, we take a 7th from the series with a 7, and we take 1 from all of the others. And when you multiply them together, you get 1 over 42. Just to show you that it wasn't a trick, I shall do it with another number chosen at random, which is 1 over 80. And this time, 80 is 5 times 16, 5 times 2 to the power of 4. So how do we get the 1 over 80 out of this product of series? Well, we want a 1 over 2 to the 4 here. We take a 1 from the next one. We take a 5th from the series for the 5. We take a 1. We take a 1. Okay. So that we've got an identification here between this series and the series, the harmonic series in the top, and a product of series here. Sorry, the pointer is so close to the... There we are. To a product of series 1 for each particular prime. All right. And that was the one that I just showed you, the 1 over 80. Now, what you can actually do is to show what the sum is of each of these series. For those of you who have seen it, it's called geometric progression. For those of you who haven't seen it before, it is very magical. We want to be able to sum this series, for example, 1 plus a half squared plus a half cubed, and so on. So you write down, let S be the sum of it. Then you multiply both sides by x, right? And something magical seems to happen. The 1 multiplied by x becomes x. The 1 over x multiplied by x becomes 1. The 1 over x squared becomes 1 over x. The 1 over x cubed becomes 1 over x squared. 1 over x to the fourth becomes 1 over x cubed. And you're nearly about to say to yourself, aha, but what about this expression down here? That's just the series that I started with. So multiplying the original series by x gives you x times s equals x plus itself again. And you rearrange that to get s equals x over x minus 1. Now the point of showing that, it is nice, but showing it was really to reinforce the point that the original harmonic series is very intimately related to an expression involving primes. So if I apply that to the harmonic series, I get the prime 2 over 2 minus 1, 3 over 3 minus 1, 5 over 5 minus 1, 7 over 7 minus 1, times 11 over 11 minus 1. The point is the harmonic series that I want you to just hold in your head is related to the primes. The details of the relationship are not important at all. Okay. And in actual fact, this harmonic series, in fact, diverges. Its sum is infinite. It keeps getting as big as you like by taking enough terms. And in fact, this is another way of showing that there are an infinite number of prime numbers, which I won't go into at the moment. But I want to keep developing this pattern, if I may. And when we develop the pattern, we looked at the sum of the reciprocals of the natural numbers. We can look here at the Riemann zeta function. This is the definition now, the first stage of the definition of the Riemann zeta function for an integer k. And what it is, it's the sum of the reciprocals of the kth powers. 1 over 2 to the k, 1 over 3 to the k, 1 over 4 to the k. So the next slide will show you what the zeta function, that's the Greek letter zeta there, evaluated at 1 is. That's just the harmonic series, 1 plus a half plus a third plus a quarter plus a fifth. Zeta at 2 is down there. It's 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared plus 1 over 5 squared. And in fact, Euler actually evaluated this by slightly dubious means to get the answer pi squared over 6, where pi is the ratio of the circumference to the diameter of the circle. Quite remarkable. All right. And here again, what I want to do is to show you that the same approach can be taken to zeta of 2, namely that it could be written out. So the thing here, the details don't matter, even though they're so nicely presented, that we're expressing zeta of 2 here in terms of expression involving the primes. That's the crux. It can be rewritten in terms involving the primes. Okay. Which brings us to the general Riemann zeta function. Here I've, in fact, done exactly the same thing for zeta evaluated at k, where it can be written in terms of expression involving the primes. So the only thing I want you to take away here is that this Riemann zeta function so far can be connected up with prime numbers. And I went through it in reasonable detail with the case of the sum of the reciprocals. Remember the 1 over 42 and the 1 over 80. And you can do it with whatever power you happen to want to take beneath the line. That's really been the summary of the last two slides. All right. It turns out what Riemann was able to show in a paper in 1859, he only wrote the one paper in number theory, 1859, it's about 10 or 11 pages long, and you can get the original in German on the web, and you can also get a translation of it on the web. He was able to extend this definition of the zeta function not only to the integers, but in fact extend it to all of the complex plane. And the complex plane just consists of numbers, a plus bi, where I, a and b are real numbers. I is the square root of -1, and when you're manipulating with it, just every time you see I squared, you replace it by 1. And he was able to extend this definition of the Riemann zeta function to all of the complex plane with the exception of s equal to 1, because when it was 1, that was that harmonic series, and if you remember, I told you that it, without proving it, I told you that it diverged. So we've now got a function called the Riemann zeta function, defined on all of the complex plane with the exception of the point 1. And you know what it looks like at the integers 2, 3, 4, 5, etc., because that was what I did on those previous slides. So you know exactly what it looks like at those integers, and you've got in your head, don't worry about the details, it can be written out in terms of prime numbers. Okay? So this function captures something about the prime numbers. And Riemann's hypothesis was that he obtained an explicit formula for the number of primes that there are up to x in terms of the zeros of this Riemann zeta function. He obtained an expression for the number of primes up to x, that's that pi of x, remember we had the prime number theorem, in terms of the zeros of the Riemann zeta function. And for the zeros of the Riemann zeta function, there are what are called the trivial ones, which lie along the negative integers at -2, -4, -6, -8. But the zeros that he uses in the expansion, in the expression of the number of primes up to x, all lie in what's called a critical, it's called the critical strip in the complex plane, which is the numbers between 0 and 1. The complex numbers whose real part is between 0 and 1. And again, if you want to do some calculation of what the zeros of the prime of the Riemann zeta function are, you find that the first few zeros they're symmetric about the horizontal axis. A half plus 14.1i and a half minus 14.1i, a half plus 21.02 and minus 21.02, and a half plus or minus 25.01, and a half plus or minus 30.41. And the pattern that you probably see is that the real part of each of these is a half. So all the zeros where the Riemann zeta function is 0 have got real part a half. And the Riemann hypothesis is that all non-trivial zeros lie on the line x equals a half. And it's been checked, and the first 10,000 billion zeros do lie on this central line. And it's generally believed that all the non-trivial zeros lie on the line. But nobody's been able to prove it after a century and a half. And although the Riemann hypothesis may seem very technical, and indeed it is, it's exceptionally important in mathematics, and its truth would give us much better results about prime numbers. And that's not only important for mathematics, but it's also important in e-commerce. Because in modern cryptography, public key cryptography, which I think will be a topic of one of my talks next year, factorizing large numbers into their constituent primes is crucial in modern security systems, such as online shopping and online banking. So it's not just of theoretical interest, it's of great commercial importance. And the Riemann zeta function also seems important in quantum physics, where the spacing between the zeros of the Riemann zeta function looks similar to the spacing between the energy levels in a quantum system. And as Marcus de Soto says at the end of his book on the music of the primes are central to the security of the modern electronic world, and their resonances with quantum physics may have something to tell us about the nature of the physical world. And many people explore the primes in different ways, but the mention of music made me want to let you hear this audio file of the music of the primes. It was created by the number theorist Jeffrey Stoppel using the audio package in the application Mathematica, and it has contributions of the first 100 zeros of the Riemann zeta function, added one at a time in an interval of 0.2 seconds. Each note has the same amplitude and frequency as the corresponding term in Riemann's exact formula. I haven't shown you the exact formula, but each coming from a single zero of the zeta function, and then at the end all 100 zeros play together for 10 seconds. And if I and that's just an advertisement for my next lecture. Our average is typical. So thank you very much for coming. Just hit it on the button, but if anybody wants to ask any questions, do come up afterwards. I'm very happy to stay around. Thank you.